I think we can start then. If you're talking, you're muted.
Yeah, no.
Okay,
well, I think we have to just because Raf will do the start, so I think we just have to wait for Raf to join, and then we can start.
Okay, sounds good.
Maybe in the meantime, I can already say that this track will be two presentations. So first, Raf and I will start to talk about the OSLO steps and the workflow composer, and then in the second half. Joachim van den Boogaard, Chris de Munk, François Remy, and I hope I'm not forgetting anyone, will discuss the NLP related research and demonstrators that they built during the FOST projects. This is usually the time that the crowd needs to move from the central location to the different breakout rooms physically, so that also takes a couple of minutes. So I guess we haven't changed that much since the analog times. Okay, I forgot the message that we can have nicely the Murphy's Law working, so Raf might be a little delayed, but he would actually start, so I will take his place for now. We already heard him talking for a while, so we can already start now, and then maybe Raf can show up a little bit later. So, good morning, everyone. Sorry for the delay. So, as said, this will be the first presentation about OSLO steps in the workflow composer, and we will have NLP discussions as the second part of this track. So, what we will present in the first half is the general problem that we were facing. Of course, I've already explained it well, so we'll go quite quickly. Then, what was the general idea for our part, what currently exists, the work that we did, and the solution that we eventually came up with. So as Rafa already told, there is a very disjoint way of working for citizens to request certain to achieve certain results when doing a procedure. So this kind of customer journey we're talking about is quite complex for a normal citizen. And the underlying technical reason behind that is that there are a ton of public services across a ton of different organizations, and all rules are hard-coded in those very different systems. So that makes it very hard to create a smooth customer journey, and you get these problems such as duplicate effort for the citizen. You're trying to achieve, for example, moving from one city to the other. You have to fill in 4 forms, and it's as if every next form asks for the same things again and again, because all that data is scattered across different applications. And secondly, it's also not personalized. The whole feeling of I can't remember how many times I've been asked to fill in my birth date across any kind of system is probably a feeling you're all familiar with. And then finally, because all those rules are hard-coded, we constantly have outdated applications. When rules change, when laws and legislation changes, and that happens more often than we would think, all these applications need to be adapted to be able to work with this updated legislation. So that's the kind of problem we're facing. All these workflows, all these customer journeys are hard-coded, opaque, and divided, siloed in very different applications. So the idea that we were tackling in the FAST project, or at least our part, was to generate workflows on the fly from more fine-grained steps. So going from the hard-coded, high-level forms that you need to fill in, actually go into more detail, more fine-grained steps, so you can actually generate workflows automatically based on those. So, small overview of what we technically did. First of all, we provided semantic step descriptions. So, meaningful descriptions of fine-grained steps. These meaningful descriptions, for this we used semantic web technologies. Why? Because, as Raf already mentioned, this allows for interoperability across different services, different organizations. And the fact that we want to create fine-grained steps is, as I said, to optimize the workflow later on. Yes. Then, secondly, we want to optimize different journeys using taking personal data into account. So using this personal data, we can further optimize the workflow and actually personalize it based on the data that we already know about the specific user. Something is wrong with the visualizations, animations, but whatever. Second step was building user interfaces on top of those personalized workflows. This is the subject of the parallel track, but you don't have to leave. I'm also sure you cannot leave. All the tracks will be recorded, so you can always rewatch it later. And then finally, complementary to this semantic step descriptions, if all steps would need to be manually filled in or described, this would take a lot of time. It would not be scalable. So complementary to that, there's also work been done on automatically detecting these steps, which is the second part of this track. So to sum up, what did we need? So we wanted to be able to compose a journey consisting of fine-grained interoperable steps, taking user data into account, and the result of that journey should allow to generate a user interface on top of it. And for that, the technologies that we used was describing these steps using semantic web, which are also called knowledge graphs, and then generate a workflow and UI on top of it using artificial intelligence. Yes, but first, let us discuss a bit what currently exists, what we started from. So this is things that Raf already told you. There are a couple of existing standards that allow us to describe personal data, but data in general, in an interoperable way so that we can actually reuse data across different organizations. So OSLO is what Raf already mentioned, which is based on ISA core vocabularies, and you have also more common standards such as schema.org, W3C, and DCMI. So these kinds of vocabularies allow us to describe data. Secondly, we want to be able to describe these processes of these public services. And for that, we saw that currently there are a couple of high-level descriptions available for public services, things such as contact information, opening hours, these kinds of things. But more fine-grained descriptions of processes or steps are currently not detailed enough. So there are no descriptions currently available to describe more detailed steps. So that was something we had to work on in this FAST project. And then finally, to what do we want to do to describe hints for user interface generation? We were also looking at standards, and we found the shape constraint language, which is actually the way to define structure of data without actually having to provide data itself. So you could specify a user should have a first name, should have a last name, should have a birth date, and these kinds of shapes you can then use to generate a user interface on top of that. So what did we find? Coarse-grained form descriptions for these public services and data shapes to hint at the user interface. So now we can move to what we actually did in the FAST project. So the rest of this presentation is divided in 3 parts. So first I will describe also steps a bit more in detail, then the workflow composer a bit more in detail, and then some small optimizations, some small discussion on optimizations we did to create a usable demonstrator. So first of all, also steps. And to make sure that we're all on the same page, I'll quickly go to a little bit of terminology because I've been saying steps all the time. Just to be clear what we mean by this. A step is an action which can have an input and produces a specific output. And generally that changes the user's state. For example, when I go to the town hall and I want to change my address on my electronic ID, that is basically a step, and that changes my state because at the end of that step, my address is changed on my electronic ID or on my personal data graph. So that is what the state is. Certain variables with certain values. For example, the data graph that I have, my first name, my last name, my birth date, etc. The goal is a very specific state you want to reach. For example, I want to have my address changed as a goal, and then we can see all the steps that are needed to achieve that goal. Fourth, the shape is how the data looks like. And this one can be, which I discussed before, this can be used to validate which states my personal data graph currently adheres to, and to provide hints for a user interface. So I will come back to that later. And then finally, a workflow is just a sequence of steps to reach a certain goal. And that is exactly what OSLO steps models. All the different steps, states, and goal that can be used to generate or compose a workflow. So in this example, we have John, an elderly person. So that is the state that we have of John. We know his first name, his phone number, his age, etc. We know which goal he wants to achieve. And then within the OSLO steps, you can also describe all the different shapes that could be potentially relevant. So these could be all the steps that a municipality might describe. So provide your first name, provide a waste request, provide your birth date, all these kinds of different steps. And then a second part, which is part of OSLO steps, which I haven't mentioned until now, is additional costs additional weights that we add to those individual steps. Those costs allow us to actually calculate alternative paths. And we can actually calculate alternative paths personalized on the profile of the user. We could, for example, think that a more technological person would prefer to do everything online via a web application, but less technical proficient person would prefer to go to the town hall for everything. So for these different people, we could generate different paths because one path has a high cost for a certain person and a lesser cost for a different person. So how does this actually look like? This is as I said, we want to have interoperable descriptions of these steps. For that, we used RDF, which is a standard Raf also mentioned. And this is exactly a kind of technological standard that allows to create interoperable data. So your data can be joined together, whether it comes from one party or 12 different parties. RDF is built to easily combine all that data together. And so our model contains of a couple of weights. Each step contains a couple of weights, a couple of requirements, and results. So as this clearly defines the definition of a step, it is something that has a certain input and produces a certain result. And in this specific case, this is a very, very fine-grained step, because that's where we want to go, using very fine-grained steps to provide your first name manually. This one is a step that could also always be executed. There are no preconditions. And as a result, we change the state of the user, we get the first name of the user. And then if we would have other steps that would require provide first name, then we can actually start putting the steps in the right kind of order. And then finally, how can we connect this kind of step descriptions with the actual data of the user? That is what I said before, using these standard shackle shapes so that we can carry out the information, what kind of data is in the state and how does valid data look like. So this is again machine readable information. So again, this interoperable format. But the idea is that the shape on the left describes the data on the right. So we could reuse this shape for different people. So good, we now know how we can provide John with all the different steps. However, if we just dump all the steps, of course, it's not enough for an improved customer journey. So that is where the workflow composer comes in, which chooses the optimal steps for John. It sees which steps are needed for John to reach his specific goal. Technologically, we made use of N3, which is an extension of RDF, so the same machine readable language we had before, to describe all possible steps, the start state and goal state. And we use a web reasoner to do the composition. So why did we make use of these kinds of technologies? This is all about web reasoning. So this is a WebLogic N3, and I is a web reasoner, which work very well with semantic technologies. So we can actually exploit those standardized vocabularies that already exist. For example, we could exploit certain meaningful data. If you fill in your family contains only of one person, you can actually use this information to guide the workflow composer to actually skip a step to ask for the data of your family members. Because if you are alone in your family, we already know your data, so we don't have to ask for any additional data. And then secondly, because this is all web logics and semantic web technologies, all steps can be published decentralized. So actually, we could use the same kind of web reasoner to reason over steps that are all locally, but also steps that are published across the country or the whole world. So this kind of technology allows that by design to publish your steps decentrally. And then final technical detail. So to actually calculate the workflow, to create that workflow composition, we describe it as a routing problem. So this descriptions and also steps are used to automatically calculate the different kind of routes. And for that, we needed to translate those descriptions into a format optimized for route calculations. So technically, how does this look like? We basically try to find paths within certain limits. So those weights or those costs that I mentioned before, those are the limits within which we want to reach a certain goal. So we could have 5 steps that all have very little cost, or 1 step that has a lot of cost. So we could create multiple alternative paths with multiple different costs. And the result is a set of alternative paths, where you basically have an ordered list of necessary steps, and then you have the values for those different costs. Very shortly about optimizations. I won't go into too much detail, but once we apply this to the moving use case, where we actually have a lot of steps that are, some are very much related to each other, some are very independent of each other. A first problem that we came across is those alternative paths. When you take order into account, you get way too many alternative paths. Filling in your first name, then your last name, or vice versa, are basically two different paths. But of course, for a user experience point of view, this is not that important. So we actually optimized to ignore permutation, to ignore order of independent steps in validated workflows. And then secondly, we also saw if there are a lot of independent steps and you don't have any hierarchy, you basically dump a lot of different steps to the user. Fill in these 50 form elements. And that's, of course, a bit of a chaos, also from a user experience point of view, but also from a performance point of view. So we included hierarchies. So this not only can hint for the user interface, so you can group certain steps together, but it also gives optimization possibilities for the workflow composer. You could first calculate high-level steps on a journey level and then drill down into more specific steps. Summing up everything, what we eventually did to create a demonstrator, which is mostly demonstrated in the parallel track, is we created a workflow composer API. So a web service generated based on those step, state, and shapes descriptions. So at any moment, a user can provide his or her current state and then request what is the next optimal step, or which options do I have right now to complete my user journey. The workflow composer optimizes based on the available steps current state and returns the following best next step. And that could be a high-level step, and then, of course, more detailed sub-steps also need to be calculated. So to sum up, I am John, and I'd like to know what do I have to do if I want to request a couple of trash cans. I go to the workflow composer. The workflow composer takes all these different steps from all these different municipalities, organizations that could be all decentralized all over the world, but probably mostly in Flanders, and then picks the very best step personalized on my user data. And after all this technical mumbo jumbo, what is the result? Hi Bob, thanks for logging in. Could you please provide the amount of trash cans you need? And this might feel like a kind of an anticlimax, but that's exactly what we wanted to achieve in this FAST project. Automatically generated workflows, optimized and personalized. And I'm sorry, Ref, I had to steal your introduction, but would you like to have some final words?
Yes, thank you for covering the introduction. They had some problems to move me to this room. So to conclude, as we all know, that at this moment, a lot of workflows are still hard-coded and then proved with this technology demonstrator and with the support of the whole FAST team that we are able to automatically create these applications based on the decentralized algorithms. Therefore, we created a method to create not only the algorithms using the method of OSLO steps, but also compose the workflows based on the live events, and also from the workflows automatically create the user interface using AI. So to conclude, this demonstrated showed that it's possible to generate automatically the workflows, but not only to create a workflow, but also to personalize them, to tailor them to the user, both on the level of the journey. So it's a tailor-made journey based on the information we have, the evidence for the public service, as well as a tailor-made touch point, whether it's chat or voice or forms. And I'm fully convinced that this solution will be a cornerstone of public services in the future, as well as private use cases such as mobility as a service, where we face the same problems and we have the same opportunities for fast. So I would like to thank you for attending this session. And I would like to thank Ben for the eloquent pitch, and we're looking forward to your questions or suggestions. And as we are in a small group, you don't need to put it in the chat, but you just can put your mic on. Are there any of the participants that face the same challenges in their daily life or in their organization?
Ralph, I'm sorry, but since we are a bit over time, I would like to move to the next presentation.
Okay, great.
Chris?
Yes, you can hear me. I think you have to stop presenting because I cannot start my presentation if there is already a presentation running.
Yeah, sorry.
Okay. So, presentation is being downloaded. Do you see the introduction screen?
I personally don't see it yet.
Okay, that's not good. Can't display content. Okay, I'll have to log in again, apparently, and that's not good. So probably still don't see it while I log out and log in, but then I have to move to the room again. Damn it.
Chris, while waiting, should we switch presentations or?
My presentation requires Chris' presentation, but if yours can go, maybe you can try.
Or might it be an option that Ben is sharing your presentation and gives you control, Chris?
I think Chris just logged out.
Ah, okay.
Joachim, if you are talking, you are muted, so we should probably restart the presentation.
Okay, sorry. Yeah, my mistake. Okay, so yeah, so what I was saying is that I will show how we bring the concept from FAST to the European level. So we applied for a grant at the European Commission, and we were able to valorize the things that we did during the FAST project at the European level. For this, we started the CEFAT for Cities project in cooperation with the Fireware Foundation, who provide the context broker for smart cities, and we have use cases in Brussels and in Vienna. So, sorry for my being muted, but if you look, we had a look at the problem size in Belgium with this nice map showing all the cities. If we project this at the European level, then we see that the problem becomes even bigger, because from our understanding, Belgium is doing a good job. But if we look at it at the European perspective, we see that there are still countries that are ahead of us, and also countries that are behind us. So the solution would be to bring the fast tools to Europe to make sure that the countries that are lagging behind and still have paper workflows, that they can catch up. And the other problem is at the European level that this should occur in multiple languages. And you see the blue dashes show the implementation of e-governments in local languages, but the orange ones show it across multiple languages. Most of the time it's only English. So we will what we will be demonstrating is something which works over different languages. Then to make all this true, we had the opportunity to create a roadmap which will be far more involving, because we from experience we know that it's really difficult to tell everything that we've been doing and that we are doing to cities. So the roadmap will consist in explicitly in creating a co-creation track with the smart cities. So I will be showing a very short movie to explain what this entails, because we want to explain what we're doing. Then also we will be integrating with the context broker. So this is the Internet of Things network that is available for smart cities. This will allow us to publish all the information that we collect over this local network. And since it's implemented already in a couple of cities, this gives us a good starting point to just publish all the information we have. And then yeah, the demo itself will be about a tool that is used to collect all the information from cities and turn it into CP-SVAP RDF, so that the workflow optimization that Ben has showed can be applied to it. And then finally, we will be holding hackathons in 3 cities to ensure that people are aware of the project. So without further ado, let me quickly show the movie that we created for the cities, just to tell them what is going on. So here it goes. For a moment, let's imagine what Google for smart cities could look like. If you go to Google right now and search for how to obtain a passport, the answer you get is already pretty nice. It contains a list of steps right on the search page. You either follow these steps or you use the link to click through. Unfortunately, the result you get only applies to US citizens. Let's try the same for, say, Ghent, the city I live in and from where I am typing this query. The first result is correct and leads me to the information I am looking for, but it lacks the nicely summarized layout. In addition, I am directed to a Dutch website while my query was in English. Unless you speak Dutch or you use a translation tool, the content is not of great help. Now, here's an idea. What if we could make the search page look like this? A nice overview in my own language is presented and gives me focused access to the information I need. The results page lists all the required steps to be taken and is actually a summarized, structured version of the website we visited earlier. This summary tells me that I need to be a Belgian citizen, I need to bring some money, depending on how urgent the request is and on how old I am, I need to bring a recent picture, and so on. There are two interesting questions we can ask here. The first one is, how does Google create a summarized version of all the web pages it collects? The second, more important question is, should we rely on Google to extract this sort of information for our cities? Or should we take control over the discoverability of our city's public services instead? This is where the Cepheid for Cities project comes in. In this project, we want to make public services discoverable for EU citizens in their own language, from anywhere, not just from the Google search page. We also want to do this for any app developer. If we succeed in doing this, lots of opportunities are created. For example, it will be possible to create truly intelligent chatbots that can be deployed at any city. The bot will not only understand that you are looking for a passport, it will also be able to connect the dots for you. It will tell you where you should get the passport, how much it will cost, what the conditions are, and so on. In other words, chatbots will not only recognize what people are looking for, but thanks to the structured information the Cepheid for Cities project will create, they will also be able to understand which steps must be taken and guide the citizen through public service processes. To achieve all this, we put AI at work. We teach the AI how to recognize public services across cities and languages. We use the Ceph e-translation service to assist us in obtaining multilingual training data. We use the Ceph context broker to publish all information on local smart cities networks. By doing so, we will effectively create a European Internet of Public Services. Okay, so this is the short introduction that we created for the smart cities, because if you want to go with a complex application like this to the cities, then it's really important to show them something what they can work with. And of course, this is a bit of a vulgarized version of what we've been doing. But the second thing that we want to show them is this application that helps in transforming their data. And I will quickly go through this so that we have enough time for Chris and Francois. So basically, the whole application is a dashboard that gives you control over your data from the beginning to the end. So what we have here first is a catalog of web pages that are being scraped by the system in the background. For example, let me show you the sources. So these are the city websites that we have been scraping in the background. And for each of these websites, we apply classification. What we want to know is we want to look for pages that contain public services. So as you know, city pages can contain news items, traffic info, and so forth. And an auto classifier tells us which pages are really interesting to harvest public services from. And we can, and the idea is that this dashboard is used to, for example, let's have a look at this one here. This tool is used to say, for example, that we want to see this here. You can have an attachment here. So this is a page in its context, and we decide this is not really useful. So what we do is we just reject it, and of course you can change that to accept them. But the idea, the general idea is that people can use this tool to classify pages, and as they go along, the classification becomes better and better. Then we have also term extraction, because what we want to do is after we have extracted the pages, we want to extract all the entities that are present and that can be used for our vocabulary. And for example, let's have a look at this one here. So we see that a term has been recognized, and we see here all the pages it occurs in. So again here, it is possible to accept and reject all this, and the idea is that you build all you assure that the system gets better over time. And just to mention this, we are doing this not only for Dutch, but in a Belgian context, we're also using this for French and for German and English. And in the European context, we are currently working with Slovenian, Italian, Norwegian, and Croatian. But then we go to the most interesting section of the tool here. So once we have harvested everything and classified the pages, once we have extracted the terms or the concepts within the vocabulary, it is time to glue everything together in the CP-SVAP vocabulary, which is a superset of OSLO, and CP-SVAP stands for Core Public Services Vocabulary Application Profile. It's the template for structuring a public service or expressing a public service in machine-readable format. So what we do here is we have extracted all the terms, and the next step is to extract the public services procedures from all these texts. And you see here that we already have a couple. This is from the website of Vienna. And the nice thing is here, we are currently just at a general, this is work in progress, so we're currently at a general public services tab and a contact points tab. And in the public services tab, it is possible to look, for example, for public service which is issued by the accounting department, for example, and then we look for here. So these drop downs are being filled out dynamically. They are connected in the backend with an RDF store, which has all the information that we're seeing right now stored in RDF format. So if we, for example, take a look at this one here, this is a result, and we open this in a new tab, then you see that we go here to the public services page. I'm going to translate it to English because my German is quite awful. So this is about the employer tax, and we see here that the competent authority is the account keeping office. So what is still on the to-do list? Well, we want, of course, to get the parsing of all these entities and that participate in this CP-SVAP profile. We want to get them better, and the idea is also here that through the validation of whatever is in our application by end users, that the systems become better. So that's it for my presentation. I am happy to receive questions. You can do that through email. And yeah, then I think it's time to return the floor to Chris and Francois. Thank you very much.
Okay, next attempt. Does anybody see the slides now?
Yes.
Yes.
Okay, so then we go for the, given that we lost lots of time, for the super short version. So this is an introduction to natural language processing. And the idea is not to make you experts, but just to have a high level understanding of modern natural language processing. So how does a computer cope with natural language? At this moment, how intelligent are they? What is needed if you really want to tackle an NLP task and having realistic expectations? So as a human, we always think we are the smartest of the bunch, but if you look at all the capabilities, well, most animals are also pretty good, but there's one thing that we still beat them on, and that's language and speech. So we can convey complex thoughts, we can reason with abstract symbols. The animals still cannot do that. So that forced one of my colleagues to state that language may be the key to true artificial intelligence. So, and nowadays we see that the computers start to become extremely potent as well. So the talk today will try to give a little bit introduction of how they do it and how capable AI is today. So one nice observation was done by Moravec, and that's basically if humans are good at something, then typically computers are bad at it, and the other way around. So computers typically are very good with math. They're also very good at exploring huge search spaces, exploring lots of options. So they kind of beat us with chess nowadays, but we still beat them on everyday things like walking around. Even with the best efforts of Boston Dynamics, a small child still beats these very complex robots. And it's the same with natural language. At this moment, we most of the time still beat NLP, but it's getting closer and closer. If we look at NLP, there is one thing that we should not forget, and that's that humans, even if we all think we are the experts on it, it took us a long time to get there. We had a lot of education. We started from a very young age to learn language. It took us 3 years of kindergarten, 6 years of primary school, and even 6 years of secondary school to learn enough about language to be able to talk about everyday topics and have real discussions and have things organized and so on. So humans, yes, we are good at it, but it takes us some effort. How do machines do it, and why is it all going so fast nowadays? Well, why it's going, what are computers doing? Well, they basically learn from examples. And it's all about deep learning. And why is it that all the rage today? That's because the compute power became available. So thanks to people who play games, you now have lots of compute power to simulate real life, and that includes human brains and artificial brains. So it really helps in speeding up things. A second equally important thing is we now have the internet and we have access to huge amounts of data. So how does a computer then, with the compute power and all this data, start to learn things? Well, we go back to a very old hypothesis in linguistics. And as they eloquently phrased it in the 1950s, a word is characterized by the company it keeps. So a word basically is defined, so the meaning of a word is defined by how it can be used in a sentence. And the idea is then to collect lots and lots of sentences, so lots of text. And on the internet, you find Wikipedia, you find lots of newspapers, magazines, you find books, you collect all of them, and you have a huge extent of material, even more than people can ever read or hear in their whole life. So it's typically multiple lifetimes of text materials. And then you learn from these texts. So we have the words, we have them embedded in sentences, so we have the company they keep, and they will try to learn from them. The aim is to assign a vector to all words. Why? Because the computers are good with mathematics, so we're going to go to mathematical concept vectors. You place all the words in a vector space, and things that have similar meanings or related are close together somehow in that vector space. So the meaning is related to the location in that vector space. How do we do that? Well, as I already said, we collect text. Next thing is we mask 20% of the words. So that's the black words, they're gone. And now the machine has to learn to predict these obfuscated words, so these masked words, from all the other words, so from the context. The nice thing about this whole learning approach is that we need no extra labeling of the material. We just need plain text and the machine can learn from it. In reality, this task was a little bit too complex to start with, because if you say all words can influence one word, you get lots and lots of dependencies. So in the beginning, they simplified the problem. How did they do that? Well, the first simplified form was bag of words model. And then you say the context is, for example, 7 words. We mask the word in the middle and we try to predict it given the 6 surrounding words. So that's a lot simpler word based on n-grams. So you have a number of words as input and we try to predict the middle word that is masked. Of course, the reverse can also be done. We know the middle word, try to guess the words around it. That's called the skipgram. The model to predict these words, either via the bag of words or via the skipgram, is a very simple model. And it's important to keep it very simple, linear, and then one non-linearity to make probabilities out of it, called a softmax. But the fact that it's linear has a very nice property that you can do mathematics in that space. The second thing is, given the local context, so previous slide, we only looked at a very local context, so 7 words around that word, 6 words basically, 3 to the left, 3 to the right, means that this whole vector space will encode 2 things from linguistics, namely syntax, which is mainly governed by local relations, and semantics, which is also largely governed by local relations. With the result, what can we do? We can, for example, look at near words. So if we look anything in the neighborhood of several, then we see that we have other things that quantize a number of items. If you look at things in the presence of a director, we get other leaders nearby. Since I said we can do mathematics on it, we can add and subtract. We had a linear model, so adding and subtracting has a meaning, and we can do computations like a king minus a man plus a woman. That's a queen. And automatically you get very close to queen. The syntax is also modeled, so if you have a plural, then you will get very close to the plural form. So you can look for analogies using that simple model. Some more examples just to show what these systems are capable of. For example, if you know that the currency of a certain country is the one thing, you can look at up from another country. So you can go from Angola and the Kwanza, which I didn't know, to Iran and the Rial, which I did know, or the other way around. There's still some limitations. We have a local context, so we have syntax and semantics, but homographs are still not solved. For example, a bat, the flying creature, or a bat where you hit balls with, or a trunk, or a park, parking a car, playing in the park, and so on. It's typically governed by longer context. The whole story has to make clear what kind of bank we're talking about, river banks or a financial bank. Another example is co-references. For example, if I have a sentence, yesterday I met an old school friend and his wife, and if I later say he, then you automatically as a human know that it refers to old school friend. And if I say she, you know that it refers to the wife, because you're smart. But computers can learn it as well if we incorporate the longer context. How do we do that? Well, we look at the surrounding words a lot further away, and we give attention to some words where we think it contains relevant information. So that's the attention mechanism. That's part 1. So all words are replaced by their vectors, and then with that vector, we look in the surrounding parts at other words that may influence that word. Instead of having one mechanism of drawing attention, you can have multiple ways of drawing attention. That's the multi-head attention that improves the system. And then you organize that you do that for all the words in the sentence, and you do that over several layers, and you get something called a transformer or a bidirectional recurrent neural network. And that's a deep approach, and it basically enriches this embedding, which encodes syntax and semantics, with information from the surrounding words. So then, for example, if this was bank, now you know which kind of bank it is, namely the financial or the river bank. If this was he or she, after going through the whole network, you know that he or she refers to the wife or the friend, for example. So the co-referencing will get extra information. So what do we need to get that far?
Chris,
yes?
Given it's 46 and we have to merge rooms in 10 minutes, I think it's maybe time to switch to demos. I think.
Okay, well, you have seen most of the things. The important thing is you need more task-specific labeled data and also something called transfer learning, but Francois will give the explanation when needed.
Okay, so Chris, can you stop sharing screen?
Yep.
Okay, share my screen. The entire desktop. Okay, so I will try to be quick since we don't have a lot of time. But basically, the main demo for my presentation is this idea of like how to use this NLP and try to help these goals that we have set for us of being able to automate journeys. Very quickly, so we noticed that the OK paperwork is very slow and costly. So we want people to be able to avoid this as much as possible. And that's why we have OSLO steps. With OSLO steps, we describe all these process and forms in ways that are standardized. That's great, but the main issue we have with this is basically that this is not what organization and municipalities have today. Today, they have a variety of forms written in a different set of technologies, and it takes a lot of effort for them to convert these forms into these new standards. So this is where NLP can help us, because we can take these forms the way they exist today, like for example in this demo, a PDF form, and then convert it as much as possible already into this new standardized form for the municipalities so that they can actually save time. The demo I'm going to show today, I'm going to explain a little bit how it works. So the first part of this process is to find a lot of forms that already exist, because you want to know what a forms looks like. What kind of fields talk about what kind of objects, or are they grouped together? For example, you want to know that, for example, if you say children, you may also mean, for example, the amount of children, in which case it's a number. But if you talk about the email address, you want to have an input field that's adapted for email addresses. So this is something you can do by doing the work of existing already existing forms and converting them to the new system. So you can use this work to improve. And the good thing is, the more people do this conversion process, the better the automation work. The other thing you can also do is use ontologies like ISA and OSLO. So they already describe objects and their properties. So based on that, you can kind of reverse engineer what forms about these things will look like. So that's the first thing. You want to have an idea of what a form looks like usually. Okay. Then now you have one example of a PDF form. How do you convert this PDF form into something meaningful in the system? Well, the first thing is you need to extract the text from these documents and detect the field names, like for example, first name, last name, address, bank accounts. You detect all these entries in the documents, and you can use either like the text itself to recognize these things. But you can also know that, for example, in a form, if you have something and then you have a white space after it, probably it means that this is a question. So this is step 2. So now we have this document that you convert into a list of questions. And the last thing you need to do is take these documents and convert it and map it to what you already know about forms. So this is where you can use word embeddings, because basically you have field names. And very often they will not be exactly the same as the one you already know, but they will be close from there. So using word embeddings, you know concepts that mean roughly the same thing, and then you can do this mapping together. And of course, when you know what fields mean, you can also try to group them. And the grouping works by knowing which groups usually work together. And the less groups you need to describe the form, the better usually the description is. So I'm going to make a small demo of this project. So this is a small website I made to demonstrate the technology. So let's go straight ahead and load one of these PDF files. Of course, that should not work. That's wonderful. Yeah, I'm sorry, this is kind of stupid. Oh, come on. So I'm sorry about that, but that's what happens when things are a bit slow. Okay, so well, I will have to start again, of course, but anyway, sorry, the loading takes time. It's just really it's supposed to be really. But okay, I can already describe what's going to be going on. So when you open a new file, it will try to do this process of reading the file, converting it into a list of fields, and then converting that into a working form. Ah, come on. Okay. Okay. I need to do that here. Okay, so here we go. So this is the PDF document. From this PDF document, we extracted the name of all the fields. And this is not only about like extracting the names, because for example, you can see that for each of these fields, we have documentation and we map this to OSLO. So that's the vocabulary from the Flemish governments. So each of these fields is mapped to the concept in OSLO. You can open this concept and go see what they are described in the data blender.be. But more than that, you can provide facilities, like for example, for nationalities, you can have a list of existing countries. Yes, for datum, you will see you can have a calendar show up, things like that. So, but even further, so you can do a lot of adaptation, like for example, automatically recognizing things. So in this case, I integrated with the browser auto-completion. So in this case, you can see that quickly by clicking on this, most of the fields are filled by the browser, which is like a super useful feature. Yeah, so that's mainly, just wanted to give another example, which is a bit more interesting. Sorry, it's going to take a bit of time because that's the first time the model runs. But so in this case, I have a list of fields that have been loaded. And you can see that some of these fields are not clear. For example, naam can be either actor naam or voornaam, but with the fact that we already have family naam in the list, we know that that means that naam must mean voornaam. So this is basically how this mapping is done. But even further, we can do things like, for example, Gmail. We know that Gmail is very close to email address. Bank reckoning is close to the IBAN bank reckoning number. And we can do a lot of things with this. Like, for example, of course, we have also this auto-completion. But more than that, we can also, if you have on a mobile phone, show the appropriate keyboards. So you see that if you open bank reckoning accounts, you get all the numbers to easily type your account. But if you click on email address, you have a keyboard that contains the @ symbol. Same, for example, for authors, you can have a list of well-known Dutch authors. But you can also see that things like aantal copies, the system can detect that this is a number, so it will automatically show you a toggle. Or something like heeft een reservatie nodig, converted into a toggle. So it's important to know that this is actually smart. So heeft een reservatie nodig is not in the train set, so the system has never seen that before. But just by analyzing the text, it can infer that it probably means that this is a question that can be answered yes or no. Same for begin datum and end datum. You can see automatically the system will show keyboards. Yeah, I think that we are pretty much out of time, so I will not be showing other demos, but that gives you an idea of what we can do with NLP. So again, just to summarize very quickly, we start with a list of fields, and then we are able to use machine learning to convert them into these forms automatically. Where you see fields are basically grouped, mapped to the OSLO ontology, and already ready for auto-completion in the browser or any other source of information. So I think that's the demo I have for this project, and if I think that it's probably time to give back the room to the main session. But if you have any question, of course, feel free to send us an email or get any information.